Let's keep sharpening our tool for series FRQs, or just series understanding in general. So let's look at the 2018 number 6. Remember, you're always going to end it on this, so don't leave a bad taste in your mouth once the AP exam's over because you stink at series. You don't need to stink at it. Let's keep reviewing it. So they're giving me the Maclaurin series for the ln of 1 plus x. So that's what this series is. On its interval of convergence, this series converges to the ln of 1 plus x. Let f be the function defined by this. So they want to take x times the ln of 1 plus x, or x over 3. So they want me to plug in x over 3 multiplied by x. So they just want me to manipulate this series for f, this given series for f. Look, I know a little bit more about this graph. That's something, I kind of already know the interval convergence of this thing. Think about this. So when x is 0, so this was shifted 1 to the left. So when x is 0, ln is 0. And then my vertical asymptote is going to be at x equals -1, right? So I know this series here only has a radius of convergence of 1. It'll have a closed right endpoint because ln's continuous over to the right side, but it's not going to be continuous at the vertical, right? So doing a vertical stretch by a factor of 3 should chop that down to 1/3, right? Or actually, I'm sorry, the 1/3 will give us a vertical stretch of 3. Or a horizontal stretch of 3. So that should probably mean the radius of convergence of this thing is 3 now. We'll prove it. Write the first 4 non-zero terms and general terms of the Maclaurin series for f. All right, here we go. Let's build it first. I think you're going to see some patterns coming here where we're going to manipulate the series they gave us by taking x, and I'm going to substitute now this series in for 1 over x, but anywhere I see an x, I'm going to plug in what? X over 3. So my first term's x, so I'm going to plug in x over 3. Minus, I'm going to take x over 3 quantity squared over 2 plus x over 3 cubed all over 3 minus x over 3 to the 4th over 4. Now I'm just going to do plugging in. Like, I'm not going to bring the x into my general term, but I can do to the general term what I'm doing to all the other terms, right? I'm going to take my x value and I'm going to plug in or plug in x over 3 and raise it to the n power. I'm going to split that out. That'll give me x to the n all over 3 to the n all over n plus dot, dot, dot. So you can see on this one, they're doing the general term all in one nice little clean series or summation. So now I can kind of chop this thing down, distribute my x, and clean it up. So my first term would be x squared over 3. I would get, what, 9 times 2 is 18, so minus, now remember that's x squared times the x, so that'd be x cubed over 18. Don't forget we're distributing the x. And this would be x to the 4th all over 27 times 3 is 81, so plus x to the 4th over 81. Okay, minus. This would be x to the 5th, x to the 4th times that x, don't forget about it. 3 to the 4th, or 3 cubes 27, 3 to the 4th is 81, 81 times 4. Let's say my brain doesn't compute right now, and I don't want to get this wrong. I'm just going to do some elementary multiplication over to the side, some old school, make sure I'm good. plus dot 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 plus. Now remember, the only thing I'm changing now to my general term in this parentheses is I'm multiplying the x to it. So I'm going to add 1 to the n using my exponent rules. If you don't know that, then we've got bigger fish to fry. All right. So the top would be x to the n plus 1. we're going to flip and multiply, so the 3n is going to come down here and multiply to the n. And then plus dot dot dot. I welcome that. I mean, manipulating series isn't that hard. All right, now this is where if you didn't get this, you're not going to get this. All right, determine the interval of convergence of the Maclaurin series for f. Like I told you, I already know what it is. Most of the time, it might not be that simple. Based off of the original graph ln of 1 plus x and my understanding of that graph, I know that the interval of convergence for f is, now remember, I did a horizontal stretch by a factor of 3. Normally this would have a radius of 1, so I'd have to triple it, right? So I would have to go to a radius of -3, centered at 0, obviously. And then I know it's going to be continuous on the right-hand side just because of how ln. This is going to approach the vertical. This isn't, so it's going to be continuous there. But I need to prove all of this. Let's do it right now. So let's do a ratio test. Just trying to get you to think. All right, so I need to do a ratio test with my f, right? My f. So if you didn't have the general term of this right, you were kind of dead in the water anyway. You actually could have gotten this point if you would have thought deeper about the graph to begin with. So the limit as n approaches infinity. Remember, this is all fundamentals of geometric series right now. If we take the next term divided by the previous term from that, it should be less than 1, right? The absolute value is the limit as n approaches infinity. So I always skip a step. I always just take the general term and I add 1 into it. And then I multiply that by flipping the original general term because that's me dividing by it. So I'm just kind of setting myself up. But remember, it's the general term of this to the right. So flipping this, n times 3 to the n. And then my -1 to the n plus 1 would flip down along with the x to the n plus 1. But now I need to plug in n plus 1 wherever I see an n, right, for my ratio test. So the top would be -1 to the n plus 2. This also would be times x to the n plus 2. All over n plus 1. And this should have been 3 to the n, so I apologize on that. I would have caught that, though, because I know what I'm looking for. This would be 3 to the n plus 1, but I need to be a little more careful when I'm doing this. So that was 3 to the n as the exponent. I'm not perfect. I'm doing these all in one cut. I don't care. All right. Making mistakes happens. Math is not always going to be nice and neat all the time. Now remember, that ratio has to be less than 1, the absolute value of that, right? It's kind of how we check a geometric anyway. Mistakes were made. I didn't fix this one either. My sincere apologies. But it's fixed now. To see if it converges. So let's think about this now. Let's break this down. I'm taking the absolute value, so my -1s and the n plus 2, I mean, none of this really matters. the absolute value is going to wash that out. N behavior models of the n over n plus 1 is going to wipe that down to a 1. So really what I'm left with is the absolute value of, when I divide these two like bases, I'm going to get x on top. When I divide these two like bases, I'm going to get 3 to the first on bottom, which would be less than 1. You can kind of already see this thing building itself, which would take me to just multiply 3 to the other side. Absolute value of x is less than 3. But my thought process was right. My radius is 3, my center is 0. The problem is I need to go a little bit deeper with checking my endpoints. Now I'm going to try to fit this in. So remember, we're going to check our endpoints into the general term. So let's plug in x. Let's plug in the right endpoint. Let's plug in x is equal to 3. And we're going to plug this into the general term. So that'd be, don't forget the sum on this. Sum as n equals 1, or the sum of n equals 1 to infinity. Wherever x is in this general term, that's where I'm going to plug my 3. So I'm going to have my negative 1 to the n plus 1, all times 3 to the n plus 1, all over what? N times 3 to the n. Well, that would give me, and I didn't take away, now look, I didn't take away my alternation, which is actually kind of helpful. So that would be negative 1 to the n plus 1, or, and yeah. All times 3 all over n. But this converges by the alternating series test. Even though I'm going from 1 to infinity, I have a harmonic, right? But I'm alternating it. So the alternating series test is going to help me on that. So that converges. That's why I need my equal to there. Now let's plug in x is equal to negative 3. I know I didn't leave a ton of space, but who cares? All right, general term. Plug it in. Now I kind of already know what's going to happen with this, right? Let's talk this out, because I'm not going to show a bunch of work on this one. So if I plug a negative 3 into here, right, negative 3 to the n plus 1, I can pull out a negative 1, right? So a negative 1 to the n plus 1 times negative 1 to the n plus 1 is going to give me, it's always going to give me a positive. So I don't even, it's not going to alternate anymore. That's going to wash out. And you got to think about that a little bit deeper, because I'm plugging negative 3 in. So I'd be left with negative 3 to the n plus 1 all over 3 to the n, right? So, I'm sorry, this would all wash itself out. So what I know that this becomes is actually 3 over n. And if you want to break that down a little more, but this is gonna come out to 3 over n. This was 3 over n alternating. Well, we know that this diverges by a direct comparison test. So you would just set up a direct comparison test, but I don't think they want you to even show that. Just state that you know that it's that and it's that. I think you'll be okay. If you have time and you want to go back and kind of formalize some things, then do that if you want. All right, let the fourth degree polynomial for f at x is equal to 0, all right, be the fourth degree Taylor for f, right, for f. use the alternating series error bound to find the upper bound for this. All right, now notice, I told you. Let's just write down upper bound I'm having some hard time writing some things today. Upper bound for, now remember, whenever you're doing an error, you always want to start with the absolute value of the difference between whatever, in this case, the 4th degree polynomial for f minus the actual function value for f at 2, right? Now they're saying, what is it? Like, we're not trying to compare it to anything. We're just trying to see what is the, find the upper bound, right? The upper bound is the max bound. So, again, if I'm using a 4th degree for f, I'm going to use the 5th degree term to plug in 2. But I'm taking the absolute value of that. Well, that, I'm going to do that down here. So that would be what? 32 all over 324. I can divide 4 into that, right? That gives me 8 and then 81. So I don't, it's not going to reduce anymore. And if it does, just keep reducing it. So that would be the upper bound for the alternating series error for my f. A little sloppy on some things. I apologize for that. But again, it's all about the fundamentals, and hopefully it helps us talking through this and you actually doing this.